Good morning, everyone. This is Hao Yuhe from the George Washington University. Today, I am presenting our work, Maui Black Box Edge Privacy Attack on Graph Neural Networks. Let me first introduce the background. Graphs exist and are widely used in different domains, including molecules, knowledge representation, and social networks. GNNs are neural networks specifically designed to handle graph data. In this slide, we present the fundamental framework of a two-layer GNN. The input to the GNN is a graph along with its node features. Within each layer of the GNN, node features are transmitted through edges to neighboring nodes. Each node updates its features by aggregating the features received from its neighbors. This whole operation is called message passing. The output of a GNN will be used in various downstream tasks, such as node classification, graph classification, and link prediction. In this paper, we focus on node classification. Common types of GNNs include GCN, GIN, and GAT. These models primarily differ in their methods of feature transmission and aggregation. GNNs have a wide range of applications, including recommender system, traffic prediction, and drug discovery. This work is motivated by a real-world example. We have two types of entities, companies or departments. In this scenario, Alice is a company that holds social network data, which is graph structure, and Bob holds user properties, which are node features and labels. Bob wants to enhance their service by leveraging users' social connections. However, due to privacy concerns, the information cannot be directly shared between Alice and Bob. To address this, they deploy a GNN model on a machine learning platform, allowing Bob to obtain predictions through an inference API without directly accessing Alice data. However, this model is still vulnerable to privacy attacks. An attacker, such as Mallory, can exploit the inference stage to reconstruct a highly accurate approximation of Alice's proprietary edge data by utilizing the inference API. Moreover, Mallory does not need Bob's access privileges. The attack is feasible as long as Mallory has access to the inference API and knows the node identity. In our paper, we show how Mallory can achieve her goal by providing our link inference attack, Maui. Here, let me formalize the threat model. The attacker's goal is to infer whether an edge exists between a pair of nodes in the target graph. The attacker's capability includes the knowledge of node identities and the black box access to the inference API, including the output of prediction probabilities. Let me introduce the framework of Maui. The first step to attack is to initialize random node features. Here, all the nodes share the same feature. Without extra knowledge, this process may require multiple tests and adjustments. If the attacker has the knowledge of some node features, they can simply apply the features to every node. Second, we estimate the influence value of a node pair. The influence value represents the influence of one node to the other through a GNN. In this figure, we want to estimate the influence value from node 1 to node 0. We remove other node features, get the prediction of node 0. Then we remove the features of node 1, find the prediction of node 0. With the predictions, we calculate the influence value from node 1 to node 0 by L2 norm. Finally, we repeat the step for all the node pairs. With all the influence values calculated, we reconstruct edges for node pairs with the top k influence values. Since each node can have an arbitrary number of edges, the influence value vary across nodes. As a result, comparing influence values between different nodes is not meaningful. Therefore, using a top K strategy to attack the entire graph is not accurate. To standardize this distribution, we apply min-max normalization to influence values of each node as our global attack strategy. Given that the minimum influence value for each node is 0, the normalization equation can be simplified by removing this term. We provide 3 estimation strategies in total to balance the attack performance and time consumption for different situations. The original Maui framework can be time-consuming since we need to call the inference API for every node pair. The efficient strategy can estimate the influence values from one node to other nodes collectively with limited API calls. The combined strategy uses the efficient strategy to filter out unnecessary node pairs, then applies the original strategy for the remaining node pair. The details of each strategy can be found in the paper. For our experiment, we use 6 datasets in total, 2 small graphs and 4 relatively large graphs. We use different GNN models, including GCN, GAT, and GraphSage. We apply 2 defense mechanisms, left graph and edge attention. Edge attention is proposed by us. We choose average precision as the primary evaluation metric due to the significant sparsity of positive labels in an adjacency matrix. Our work is compared against 3 baseline methods. It is important to note that each of these baselines requires additional attack capabilities. For example, LSA2 requires node features. We evaluate attack performance under both local and global attack scenarios. For small datasets, we perform attacks on the entire graph. For larger datasets, we conduct attacks on 5 randomly selected subgraphs. Here we share the performance of local attacks with 2-layer GCNs. For local attacks, we compute the AP for each node and then average the results. It is evident that Maui significantly outperforms other baseline methods, with a considerable gap between it and the others. For global attack, the upper section is the performance without our normalization strategy, and the lower section is under our strategy. Same as local attack, Maui achieves the best results. It is also evident that the normalization strategy greatly improves the global attack. This is the result of global attack with normalization strategy. Here we show the precision and recall at different ratios of predicted edges. Overall, our method achieves the best and the most stable results. Finally, we compare the performance of Maui using different estimation strategies with 2-layer GCNs. The figures illustrate the attack performance. The use of efficient strategy does not have a large impact on performance. The GitHub dataset contains dense and sparse subgraphs. However, in practice, we can adjust the hyperparameters to achieve the optimal results. In this slide, the figures display the running time. We can conclude that the efficient strategy significantly reduces time consumption without large impact on performance. In practice, we can adjust the use of efficient and combined strategies for the best outcome. For larger or denser graphs and deeper GNNs, only the efficient and combined strategies can complete the tasks within a reasonable time frame. To conclude, we have demonstrated that vertical partition of graph data and a black box API could leak privacy. We have designed a link inference attack, Maui, which attacks under the most challenging security setting. We have provided different strategies to improve the attack's applicability. We have evaluated the attack performance across various criteria, which are detailed in the paper. We have made our code available on GitHub. The artifacts are evaluated to be functional and reproducible. If you have any questions, feel free to contact me. Thank you all for listening.